Good morning to all. I am Dr. Thayalan. We are going to discuss about interaction of radiation with matter part 3, especially pair production topic. So this video is presented by Radiological Physics Foundation. So what is the usefulness of interaction of radiation with matter? It is very much useful to understand the biological effect that manifests in the human body. It also tells us how radiation is attenuated in a medium. X-rays and gamma rays have wavelength in the order of nanometer, and 1 nanometer is equal to 10 power 9 meter. They travel as waves in a medium and interact as particles. They interact with structures that are similar in size to their wavelength. That means structures having a nanometer dimension has more probability for interaction. The most common targets are electron, nucleus and atoms. What are the various types of interaction? Compton scattering, photoelectric effect, pair production, coherent scattering, photodisintegration. This left side 3 is very important for medical applications, whereas these two are not having much role in medical application. However, today lecture we are going to talk about pair production in detail and some extent about the coherent scattering and photodisintegration. In pair production, the interaction is between the X-ray photon and the nuclear field. The photon having energy greater than 1.02 MeV is passing near the nuclear field is subjected to strong nuclear field. For example, if you take the photon here and this is the nucleus, this is the K shell, the nuclear field is between the nucleus and the K shell. It interacts here where it experiences strong nuclear field. The X-ray photon disappear and create one electron and positron here. The electron goes in this direction and the positron goes like this. This is known as pair production. Pair means two particles. One is actually the electron, the other one is a positron. The energy transferred to kinetic energy is equal to instant photon energy h nu minus 1.02 energy to produce this particle. Because to produce an electron, the energy required to produce an electron is 0.51 million electron volt and the energy required to produce one positron is 0.51. If you add the two, it comes around 1.02. Hence, each particle have energy of 0.51 MeV. It is an example for conversion of energy into mass as predicted by Einstein E is equal to mc square. What is the fate of electron after this pair production? The electron here, what will happen? It loses energy in the medium by excitation and ionization as well as filling vacancy in the orbit in the medium. Similarly, what the positron does? Positron is similar to electron in mass but with a positive charge. It travels in the medium and loses by ionization, excitation and Brustolin process. Finally, the positron undergo annihilations. What is annihilation? It is a disappearance of positron. The positron combines with an electron and produces two photons of energy 0.511 MeV each. That means you can see the picture here. The positron is here. It combines with the electron and get annihilated and produces two gamma photon in opposite direction, 180 degree. So one gamma goes in this direction, another gamma goes another direction. The angle is 180 degree. This is to conserve the momentum of the collision. These photons are emitted in opposite direction 180 degree to each other to conserve momentum of the collision. So let us see the picture. The positron is coming, combined with the electron and produces two gamma photons in opposite direction and the energy of the gamma photon is 511 kilo electron volt. Positron annihilation is an example for conversion of mass into energy as predicted by Einstein. This pair production is the basis for positron emission tomography or PET-CT nowadays commonly used in medical imaging. The probability of pair production increases with the energy and also increases with the atomic number. The probability of pair production is proportional to Z to the power of 2. As the atomic number increases, the probability increases. The minimum threshold energy for pair production is 1.02 MeV. Suppose if the X-ray photon having lesser energy 1.02 MeV, it cannot undergo pair production. Let us discuss about coherent scattering. It is also called classical scattering or Thomson scattering after the scientist Thomson, J.J. Thomson. The X-ray photon having energy less than 10 kV interact with the matter. It makes the atom excited. The atom releases this energy as scattered X-ray photon. The wavelength of the incident and scattered photon is equal, hence the energy is also equal. Suppose if you see in the picture, lambda 1 is the incident photon and lambda 2 is the scattered photon. The both wavelengths are equal after the interaction. In coherent scattering, direction of the scattered X-ray is different from that of incident X-ray. You can see from the picture, this is the direction of the incident X-ray, this is the direction of the scattered photon. They are different. Scattered X-ray is in forward direction, no transfer of energy, no ionization, only change of direction without change in energy. It is important low energy in diagnostic X-rays, example mammography. It is around 12% of interaction takes place at 30 kV, whereas it is less than 5% in soft tissue around 70 kV. Coherent scattering has no consequence in diagnostic X-ray imaging because it requires low energy. Photodisintegration. In photodisintegration, the photon interacts directly with the nucleus. You can see in the picture, the photon comes here, interact with the nucleus here, and nuclear fragments are formed. The nucleus is raised to excited state and instantly emits a nuclear or nuclear fragments. Fragment may be 1 or 2. It requires energy is greater than 10 million electron volt. No role in medicine, especially or diagnostic radiology. So what is the total attenuation coefficient? The total attenuation coefficient is made up of photoelectric, Compton scattering and pair production. In one interaction, one process can take place. In many interactions, all of them may take place. The probability of each interaction is proportional to sum of the cross section. Let us see the plot. It is drawn with mass attenuation coefficient versus photon energy. It is the curve is actually upper curve is for lead, lower curve is for water. You can see the difference. At low energy, there is a lot of difference between the water and lead, and also lead is having actually the KH absorption here. This is diagnostic radiology energy where high Z material and low Z materials are differentially absorbed. If we come to around 1 MeV, there is no much difference between the high Z and low Z. This is particularly that situation where we are using radiotherapy applications, where Compton effect is dominant and photoelectric is totally absent. If you go to very high energy, pair production takes place and there is again difference between the high Z and low Z, and photoelectric is completely nil and Compton scattering role is reduced here. The overall attenuation coefficient can be described in terms of graph. You can see coherent scattering graph is followed like this. It is very high low energy and going on decreasing with increase of energy. See, the another curve is photoelectric effect. So at low energy it is very high, then quickly decreases as the energy increases. So the Compton interaction, it decreases slowly and goes over a range of energies. So the pair production start after some energy and it goes increasing as the energy increases. So if you add all the Rayleigh scattering, photoelectric and Compton pair production, the total interaction curves like this. It goes like that and that means the infrared attenuation decreases slowly and exists in all the energies. What is the importance of interactions with the energy? Up to 50 kV, photoelectric absorption is very important. 60 to 90 kV, photoelectric and Compton effect is important. 200 kilo electron volt and 2 MeV, Compton alone is very important. 5 MeV, 10 MeV, pair production begins. 50 MeV, 100 MeV, pair production alone is important. In summary, pair production involves photon-nucleus interaction. The threshold photon energy is greater than 1.02 MeV. Pair production increases with the energy and varies with Z square. Positron undergoes annihilation with the production of 2 gamma photons. Coherent scattering has no energy loss, only change of direction. Photonuclear disintegration require greater than 10 million electron volt. Coherent scattering and photonuclear disintegration has no role in radiological applications. The total attenuation is sum of the Compton, photoelectric and pair production. I hope you enjoyed the video. We will come back with a new title in the next episode. Kindly subscribe and succeed.